Now we want to talk about thermostoichiometry. All right, so we have our chemical equations, and now we have these delta H's that quantify the associated heats for those reactions. And so how we can interpret this, if we look at those units, delta H is kilojoules per mole. That is energy per mole. And so what we can then say is that for every 1 mole of C3H8, where this 1 right here matches the coefficient, that's stoichiometry coming in, of the C3H8. So for every 1 mole that reacts, 2,220 kilojoules is released as heat. So if we look at a product, say water in this case, if I have 0.32 moles of water forms, we can see that now we use 4 moles of water because there's a 4 in the coefficient. The 220 that we use is still the same as the 220 that we have right here. So we always use the reaction coefficient and we always use the number. You will note there is a little bit of nuance here that the delta H is negative. This is an exothermic reaction. Combustion usually is very exothermic. And so, but we don't use the negative. Instead, when we would write our answer, or when we talk about the answer, we would say that 180 kilojoules is released, right? So 180 kilojoules is released. We don't usually say that the heat is negative 180 kilojoules. So again, it's a little kind of nuanced. If you're using that heat and say applying it to a different calculation, you would want to use negative 180 kilojoules. So the sign convention is still confusing, and we just want to there's this kind of mix of the signs, where we use the signs, and when we describe it using language, released, absorbed, those sorts of things. We just want to make it hard. All right, so I'm trying to make it a little bit easier. Look at an example. How much heat is released via the combustion of 8 grams of ethane, which is C2H6, according to the following reaction? So 2 C2H6 plus 7 O2 becomes 4 CO2 plus 6 H2O, delta H, negative 3,120 kilojoules per mole. So let's go pop over and see what this looks like when we actually work it out. So we want to know in this case how much heat is released by the combustion of 8 grams of ethane according to this reaction. All right, so when we have this kind of setup, we can see we want to know the heat associated with a reaction. Okay? And we have this delta H that's given to us right here. Okay? And so if we start to think about, we're dealing with an amount of stuff coming out of a reaction. So we've seen this before, right? If you have a certain amount of, say, the 8 grams of ethane, that's a reactant, and you want to know something as to an amount of how much comes out of the reaction, right? How much product you get, or how much other reactant do you need, we can use stoichiometry in this regard. Okay? And so we're going to use the same ideas of stoichiometry here, that we can take our 8 grams of C2H6, I can take the molar mass. I know that 1 mole of C2H6 is 30.08 grams of C2H6. And we know that at that point in time, I've taken this mass and I've turned it into moles. We know that once we're in mole, we can start to use these reaction coefficients as conversion factors. And so what I can say is, for every, there's a 2 right there, of C2H6, right? That's per mole. And we can see there's also per mole right here. And so what we can do is we can say that this is 3,120 kilojoules. The delta H for the reaction, that enthalpy of the reaction, serves as a conversion factor to go between amount of reactant and heat released. We can think about heat released or produced or consumed in a reaction as a reactant or product. And so this 2 right here comes from that reaction coefficient still. So it is still going to be the fact that you see the 2 in the coefficient. It does need to be the 2 right here. This is 312. So if you were 312 is always the same, but if you were dealing with water, it'd be per 6 moles of water, 4 moles of CO2, 7 moles of O2. So whatever you were doing, you just take that coefficient right there. And so the grams doesn't work. It does need to be in moles. And then the coefficient for the moles is just whatever you have, whatever the coefficient, the number is in that reaction, that coefficient right there. And so if we do this out, we would get, calculate out 2 sig figs, 410 kilojoules. And so there is a smidge of nuance because you'll note it says released. So how much heat is released? So the official answer would be 410 kilojoules released. You will note there's a negative number right there. So this is an exothermic reaction, right? It's implied that this is a product. We don't put a negative right here because we use that word. We would say it's 410 kilojoules of heat released. And so we've seen that sometimes these negative numbers can be, the negative or positive numbers when we use in calculations can be confusing. So it's commonplace just to go ahead and literally use the language when we're talking about heat coming in, going into or coming out of a reaction. So when you burn 8 grams of ethane, you're going to get 410 kilojoules that comes up. That is a negative heat. It's exothermic. It's leaving the reaction, right, going into the surroundings. But to be really clear, instead of using positive or negative coefficients, we use our language, right? We say it is 410 kilojoules released. For endothermic reactions, it would be a positive number technically. You still keep the positive number, but you would say it's absorbed. You don't change. You just always basically write a positive number, and then your language indicates is it going out or coming in. But otherwise, we can see the general setup is similar to stoichiometry. One thing to note, we do just stop here. We only need to do 2 steps because basically there's no molar mass on this side over here for the heat. You're already just in the kilojoules, so you're good to go. But we can use this idea. We use the same molar mass. We can see again, still the rule still applies. If you're given a mass of something, using the molar mass to convert it to moles is still always a good first step.